Hello, everyone. Welcome back. Today, I'm going to be talking about piecewise functions. So, what's a piecewise function? Basically, a piecewise function is a function that consists of two or more functions. So, as you can imagine, when it comes to piecewise functions, it's a bit harder to determine if it's a function or not because that depends, where does one function end, where does the next function start. Things like that can be, factors in knowing if something is indeed a piecewise function or not, or if it's just a piecewise relation. Because for a lot of natural relations, they just happen to be functions. However, when it comes to piecewise functions, they can be any type of thing that we want, right? We can put two different functions together, put three different functions together, and so in order for the piecewise function to still be a function, it not only needs for every piece to be a function itself, but then when the pieces come together, it's still a function overall. Is the important part. Okay, so let's start with example one. Example one says a city parking lot uses the following rules to calculate parking fees. A flat rate of $3.50 for any time of up to and including the first hour. So basically, if you park for at least for any time between 0 minutes and 1 hour, so 0 to 60 minutes, it's $3.50. So if you don't park for any time at all, then of course you don't have to pay any parking fee if you're not parking at all. But if you park for up to 15 minutes, right? For 15 minutes or up to 15 minutes, so a quarter of an hour, it costs 350. Same with if you park for half an hour, 350. If you park for 1 hour, it's also 350. Then it says a flat rate of $10 for any amount of time over 1 hour and up to and including 2 hours. Okay, so it's $10 for if you parked for an hour and 15 minutes. Same with if you parked for an hour and a half or 2 hours, it's the same, it's $10. And then it's a flat rate of $10 plus $3 for each hour after 2 hours. Okay, so that means for 3 hours, it would be the $10 plus $3 for every hour after 2 hours, which there's one for 3 hours, so $13, then $16, and then $19. And that's all the points they want. Okay. So we're going to use a graphical model to represent this function for parking fees. Because as you can see, they changed the function a couple times. First, they're saying we're starting here, and then we're going up to $3.50 parking fee, which is right here, $3.50 for up to the first 1 hour. Let's say, I want to make this nice and to scale. Let's say this is 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. There we go. Okay, awesome. So for the first up to and including 1 hour, it's $3.50. For up to and including 2 hours, it jumps up here to $10 for parking. So it's $10 for parking if you park for more than 1 hour. And then after this point, it's just after 2 hours, it's $3. It's a flat rate of $10 and a rate of $3 for each hour after the 2 hours. So for 3 hours, it was, we said 13. Then here, and so on, right? We continue to go up that way. All right. Let's draw a line through there. There we go. Amazing. Perfect. Okay. Then it says use an algebraic model to express parking fees. And the thing is, if we didn't have piecewise functions specifically in their format, we wouldn't be able to even do this, right? Because you could say, well, but there's three different equations here. First, there's the equation that we have from 0 to 1. Then we have a separate equation from 0 to 2, and then we have a separate equation from here, right? We have three different pieces, 1, 2, 3 pieces, and so there's not just going to be one function that represents this, unless it's a piecewise function, which is a combination of, or I shouldn't use the word combination because that's something else, but that is a function that consists of two or more functions. So let's draw this in an algebraic model. So let's call this function f of x. So let's say that f of x is going to equal to 0 when x is equal to 0, right? Because if we don't park for any time, if we park for 0 minutes, so meaning we don't park at all, then we don't pay anything at all. Now let's say we park for up to 1 hour, right? So let's say we park for a time that is greater than 0 minutes, up to and including, up to and including 1 hour, so a time that's greater than no time at all, right? Greater than 0 hours, up to and including the first hour, we pay $3.50, so 3.5. Then for up to and including 2 hours, from 1 to 2, but not including 1, but including 2 hours, it's $10. And then from higher than 2, I guess we should just say x greater than 2, it would be $10 plus a rate of $3 times the number of additional hours past that point. So I'm just realizing not the total hours, so not x exactly. Let's fix that. It's not the total hours. It's going to be x minus the 2 we've already paid for, because that $10 covers the first 2 hours, and it's 3 hours for every additional hour past those 2. So it would be 10 plus 3 times x minus 2, which is really 10 plus 3x minus 6, which is really 3x plus 4. So I'm actually going to just change that to its simplified form, that this is going to just be 3x plus 4. And if we try that, then we should end up getting the right term. So let's try plugging in 3 here. If we do that, we get 9 plus 4, which is 13, which is the right answer. If we plug in 4 here, we get 12 plus 4, which is indeed 16. And if we plug in 5, we do indeed get 19. And so we have done this correctly. So this is just a way to take what the equation told us, which is that it's 10 minutes, right? Or sorry, $10 plus, 3 times however many hours we had after 2 hours. So 3 times x minus 2, we're taking that, we're just simplifying it, and we're putting the simplified version into our algebraic model. And in general, when we do have piecewise functions, we don't always have to know right away what's the simplified version, but we should put the most simplified version in our final response, right? We shouldn't have 10 plus 3x minus 2. We should have the simplest version of this line in our final response. So there we go. This models it pretty well. This basically says that if we don't park at all, then we spend $0. That if we park for more than 0 hours, but less than or including 1 hour, so 1 hour or less, but we still do park there, we don't park for no time at all, then it's $3.50. If we park for more than 1 hour, but less than or equal to 2 hours, it's $10. If we park for more than 2 hours, then it's going to be 3 times the number of hours plus 4, which is equivalent to, $10 initially for, an initial fee, plus an extra $3 for every additional hour plus 2 hours. Those are equivalent statements. Very good. Let's do a couple more examples. This one says to define this graph. So how would I define this graph? Well, looks like we have a few different parts, right? Looks like we have part 1, and we have part 2, and we have part 3, and we have part 4. We have 4 different parts. You might be saying, oh, wait, this absolute value, isn't this just one part? And yes and no. Every absolute value is really just a piecewise function. Okay, every absolute value can be expressed in piecewise function form. So it's up to us if we want to put it in absolute value format or just express it as 2 lines. In this example, I'm just going to express it as 2 lines. Okay, so let's define this following graph. So what's our first part of the graph? it would be this section over here that I'm going to highlight in green. So what's the equation of that section? Well, let's see. If we extended this line, the y-intercept would be -3. So -3. And what's our slope? Our slope is -1. So -x minus 3 for when? For when x is between, let's see, -2, 3, 4, 5, 6, and -6. So when we have an x that is between -2 and -6, that is the function we're going to go off of. Okay, now what about the second piece, which is this piece right here? Well, this one also has a slope of 1, but it's +1 this time. And the y-intercept is 1. So x plus 1 is the name of this function here, right? And then this is going to go from -2 up to +2. Okay? And then we have this section here, which says that x is going to be equal to 3, or sorry, y is going to be equal to 3 from the time x is between 1 and 3, but not including those numbers. Look carefully, there's 2 holes on either end, so that means we don't include those numbers, but everything that's in between 1 and 3 that doesn't include 1 and 3 themselves is good. So let's do that. 1, oh, sorry, this one, I'm just realizing we're overlapping. This should have been 1, not 2. My apologies. Okay, so between 1 and 3, there we go. And then we have this last piece here, which what's the equation for this last piece here? Well, it looks like this equation, if we extended this line, it would have a y-intercept of -1, and the slope is 2, right? Rise over run, just going back to basic grade 9 stuff. Rise over run is going to be 2 over 1, which is 2. So 2x minus 1 for when x is greater than or equal to 3. Oh, and actually it does, there's no arrow here, right? So actually it does stop somewhere. So let's actually write down and where it stops. So it starts at -3, or sorry, at +3, 4, 5, and it ends at 5. So, but there's no holes on either end, so it does include those numbers indeed. The only other time I didn't include the value is I just said less than here, which doesn't actually make a difference in this situation here. Right there where we said just less than, because it's continuous anyway, so it doesn't make a difference. But do make sure that whenever you have holes, that it's a strict less than or a strict greater than. It's not less than or equal or greater than or equal when you do see holes. Right? So do make sure of that. But this one, technically, we could swap this sign, this equals, and put the equals here if we wanted to. That is an option for us. Or we could do it the way we had it and put it like that. That's fine as well, because either way, x minus 3 or -x minus 3 and x plus 1 at x equals to -2, they're actually at the same point anyway. It's both going to be -1 with respect to y. Awesome. Okay, so now let's do this one. This one says graph the following function, determine if the function is continuous or discontinuous, and state the domain and range. Okay, so let's draw each part individually. So this first part says that the function should look like x squared minus 2 when x is less than 2. So when x is less than 2, which is, let's say this is x equals 2, it's all of this area, it's this whole big area, we're going to draw x squared minus 2. So what does x squared minus 2 look like? Well, it looks like our parent quadratic function, except we just start 2 lower, right? That's the only difference. So we start here, over 1 up 1, and then over 2 up 4. In this case, it's on this border line, so I'm just going to draw a dot there. And there we go. Then over 3 up 9, so 4, 5, 6, 7. There we go. And then on this side, we don't have to draw it because we're good. We've already drawn enough on this side because it stops right here at x equals 2. Then it says f of x is equal to 4 when x is 2. So therefore, we have a point here, okay, because it says f of x is 4 when x is equal to 2. So we draw this point for our second piece, which, right, is off track from our quadratic, but that is okay because this is a piecewise function that's combining multiple functions, and the quadratic is just one of those. And then when x is greater than 2, the function is 2 times the absolute value of x minus 3. So what about when it's exactly equal to 2? Well, we would have a hole there, right? So where would we have our hole? We would have our hole at, let's see, absolute value of 2 minus 3 would be absolute value minus 1, which is 2. So we have a hole at 2, 2, which actually already have that hole from the quadratic, so there's actually nothing new to draw there. What about if it's 3? Well, then the answer is just going to be 2 times 0, which is 0, right? So our next point would be at 3, 0. Okay, what if we add 4? What if we add 4 for x? That's a good question. Then we would have 4 minus 1 on our absolute value bars, which is just 2 times 1, which is 2. So for 4, we would have 2. Oh. And then for 5, it should be here, but let's see. Be 2 times 2, 4. Yeah, exactly. So then we can draw this, connect those dots. Then we can also connect these dots. And the function overall is going to look like this. So that's a pretty silly looking function, right? We might say, oh, well, what the heck is that? Well, this is a piecewise function where there's 3 parts. This is part quadratic, part just a point here that's, a wandered off point, and then part absolute value. And so this is the nature of when we have 3 separate functions, right? We have 3 different functions that are making up this piecewise function. Okay, but that's not all. It also says determine if the function is continuous or discontinuous. Well, the function is continuous throughout most of this, but the function is discontinuous right here. Oh, oops. Right here at x equals 2. So at x equals 2, the function is discontinuous, right? Because it doesn't go at 2, 2 like the rest of the function is aiming for. It just jumps and goes up to 4 and then it comes on back down. So it's discontinuous at x equals to 2. Then it says state the domain and range. The domain is what values of x are possible. Well, here's the thing. All values of x are possible, right? We can have things that are equal to 2, things that are greater than 2, things that are less than 2 in this function. So therefore, all possible domain values are there. Another way to write the domain is to write it in interval notation, which is going to be negative infinity to infinity. Now, what about the range? Does it range throughout everything? Well, the thing is, all the points down here below 2 with respect to y are never going to be met, right? We're never going to get any points down here. However, when we go here and up, we always have something, right? Especially we have those 2 arrows and they're going up to infinity at different rates, but they're both going to infinity. And so therefore for range is everything except for things that are less than 2, right? So y must be greater than or equal to negative 2, right? Because here we have negative 2 right there. It must be greater than or equal to that negative 2 mark in order for it to be part of the range. And to write this in interval notation, it would be including negative 2 and up to infinity is okay, but things that are below negative 2 are not included here, right? Because the very lowest point that we get to with any of these functions in our piecewise function is the negative 2 that we get to for our quadratic, and that does not come up again. Nothing lower than that comes up ever again. basically, in any of the other functions, in any of the other parts of the functions we're drawing. Good. Okay. So yeah, so I think that's the full question because we graphed it. We said that the function was discontinuous at x equals 2. So we said discontinuous and we stated domain and range in two different ways. So I think we are good. We have that one covered. Okay. This next question asks, is g of x continuous? Okay. So for this one, we already know that the different pieces are continuous themselves, right? Because we know that negative x minus 6, it's continuous, right? We know that any line is just going to be continuous. Same with this line. We know any line, this line is going to be continuous. And we know this parabola is going to be continuous within itself, right? Because all lines, all parabolas, and all lines again are continuous. However, the only parts that the only reason that this function overall might not be continuous is if at the times where we swap, right? During the times where we swap from a line to another line or from a line to a quadratic or back or something like that, those are the only possible points, those points where we switch that might be discontinuous. Okay? So let's figure out if that's the case. Let's figure out if that's the case. And we can do so graphically, and also we actually don't need the graph technically, although I will draw it. We can also just figure it out algebraically. So I'm going to talk about how we could do it algebraically first. So here, our ending point of this function, the point where the first function stops and the second one begins, is at -3, right? So the function is going to be -3 minus 6 at x equals to -3. Okay, so what's that going to be equal to? That's going to be 3 minus 6, which is -3. So at x equals -3, g of x also equals -3. So g -3 is equal to this, to -3. Now the question is, will our next one be the same, right? Now I know that this doesn't actually include, it just says strictly less than, not less than or equal. But in order for the function to be continuous, when we're at the point -3, that whole has got to be at the same point that our filled in dot is anyway for it to be continuous. Because if our whole is at a separate point, that means we're jumping to a different place in our graph, right? And so let's see. Let's just so in this case, we're not going to say g of -3, because of course g of -3 would go to this one, right? The first equation. But we're just going to sub x equals -3 into 2x plus 3. And why are we doing that? We're doing that to see if the whole, right? Because this is going to tell us where there's a hole. We want to see if the whole is in the same place as the other part anyway. And it is, right? 2 times -3 plus 3 is equal to -6 plus 3, which is equal to -3. So even though technically we have a hole there, that hole gets filled in by the previous equation. So hopefully you get what I'm saying here, but in case you don't, I'm actually going to draw the graph as well. So for less than or equal to -3, well, -3 is right here. We have -x minus 6. We're starting at 1, 2, 3, 4, 5, 6. And then we're going to go up to there. So our point is what? Well, our point is going to be -3, -3, and it's sloping downwards like that. There we go. Okay. So there it is. And then our next one is 2x plus 3. So ordinarily we have a hole here, right? But the hole is already filled in by the previous function. So now we're just going to start doing 2x. So we're switching up our slope, right? We're switching up our slope. So now we're having this for a while, all the way up till we get to 0, but not including 0. So I'm going to draw a hole here. Now let's see if this hole gets filled in just like our last hole does. The last part of the function is x squared plus 3. Now what is x squared plus 3 when x is equal to 0? Well, it will be at 3, right? If we start drawing this parabola, we're going to actually fill in this hole because what is this third function? Well, this third function is the parent function for a quadratic function just we just shifted up by 3. So it does start here, and then we do over 1 up 1, over 2 up 4, all of our regular um, quadratic stuff that we would otherwise do. So there we go. There we have it. Awesome. Let's make this a little bit smaller, but I do want to be clear we filled in a hole there, and then we're good. So this function is indeed continuous, right? We knew it would be continuous you know, on every interval, but in terms of between the intervals, so at the points x equals -3, that's the first point we had to check to make sure that that hole got filled in. And then same with at x equals 0, we had to check that point to see did that the hole that was going to be at x equals 0, did that get filled in by the same function. So therefore, this function is continuous, right? This function is continuous. So therefore, yes, g of x is continuous because every single hole we had ended up just getting filled in, right? Now we could also continue to solve this the algebraic way, and that would just be to plug in to find g of 0, and then also to sub in x equals 0 for the second equation as well to find where the hole is and confirm that the hole got filled in. So yeah, so personally I prefer the algebraic way, but you can also do it the graphing way, or you can do both. Or if a question does ask for both, then definitely do both. Or in this situation, even they had a graph given to us, so that kind of suggested that maybe the graph would help us, or maybe they wanted a graph as well. So good to clarify that though, because they didn't actually say and graph it. They did just say is g of x continuous, yes or no, and we concluded that it is indeed continuous. All right, well, that is everything for piecewise functions. Next day, we'll talk about rates of change. Good work today, everyone, and I will see everyone for rates of change. Bye, everyone.